Hello class, I hope you're having a wonderful day. Today I would like to take a look at a practice problem from chapter 7 where we will identify a planet orbiting the sun based off of the orbital time period data. So I'll read the problem to you and we can go ahead and get started. So a planet orbits the sun at an average orbital radius of 2.279 times 10 to the 8th kilometers. Now we immediately know that we need to convert from units of kilometers to units of meters. So by doing this, we are going to get 2.279 times 10 to the 11th meters, because we know that there's 1,000 meters in every kilometer. So from kilometers to meters, we're going to move our decimal place 3 places to the right, so that's going to give me 2.279 times 10 to the 11th meters. Okay, so in part A it says calculate the orbital time period of the planet in units of seconds, days, and years. So we're going to use the equation orbital time period is equal to 2 pi times the square root of the average orbital radius cubed divided by the product of the universal gravitational constant and the mass of the sun. Okay, so we have the average orbital radius right here, so 2 pi times the square root, so I have 2.279 times 10 to the 11th meters. We're going to have to cube that value. Then we're going to divide by the universal gravitational constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Then we're going to multiply by the mass of the sun, which is 1.99 times 10 to the 30th kilograms. Okay, and so what let's do is get out our calculator. And what I want to do is resolve the value under the radical right now. But let's just take care of the numerator and then take care of the denominator and go through there. Let's not try to just slam everything on the calculator and do it in one step. So we've got 2.279 to the 11th power. And we are going to cube that value. That's going to give me 1.18367 64 times 10 to the 34th. And right here, not only do we have to cube the numerical value, we have to cube the unit value. So cube the numerical value and cube the unit value. So we're going to have units of meters cubed in the numerator. All right, in the denominator, we're going to multiply the universal gravitational constant and the mass of the sun. And that's going to give me 1.327 times 10 to the 20th power. Now what I want to do is resolve the units in the denominator here. And the first step here is to go ahead and break down the unit of a Newton. You know that a Newton is a kilogram meter per second squared. So what I have here is kilogram times meter per second squared. So this is in Newton, okay? So we've got a Newton times meters squared, and algebraically we can write this as meters squared over 1. We're going to divide all of this by units of kilograms squared. And algebraically, we can write that as kilograms squared over 1. And we're multiplying by units of kilograms. So times kilograms over 1. Well, the first thing that we can do here is cancel this kilogram and one of the kilograms here. So right here in the denominator where I have kilograms squared, this is just kilograms times kilograms, okay? And one of these is going to cancel with the kilogram in the numerator. So I can just scribble this guy out here and get rid of that kilogram. I can also go ahead and cancel these kilograms. So I've got a kilogram here in the numerator and a kilogram in the denominator. Those go ahead and cancel. So I've got meters times meters squared. We know that this is going to be equal to meters cubed divided by second squared times 1. That's going to be second squared. So these are the units that I'm left with in my denominator here under the radical. So I've got meters cubed per second squared. Okay, I'm going to erase all of this here. All right, so what we need to do next is let's go ahead and take care of the numerical value. Then we'll take a look at the unit value. So let's go ahead and type this value in our numerator, 1.1836764 times 10 to the 34th. And we're going to divide it by 1.32733 times 10 to the 20th power. And that's going to give me the square root. So orbital time period is equal to 2 pi times the square root of 8.9177251 times 10 to the 13th power. Now let's take a look at the units here. So in my numerator, I have meters cubed. I'm going to say meters cubed over 1. We're dividing this by meters cubed per second squared. And what we need to do is remember the old algebra rule that says whenever we divide fractions, it's like multiplying by the reciprocal of the denominator. So what I have here is meters cubed over 1 times the reciprocal of the denominator. So I've got second squared divided by meters cubed. And you can see that our meters cubed cancel, leaving us with units of second squared. All right. Okay, so now what we need to do is take the square root of our numerical value and the square root of our unit value. So you know the square root of second square will give us units of seconds. Okay, so I have 2 pi times 'So this gives me 9,443,370.744 seconds. And we're going to multiply this value by 2 pi. And this gives me 59,334,448.31 seconds. So a lot of seconds here, okay? And I'm going to go ahead and write the answer by part A. So in units of seconds, our orbital time period for this planet is 59,334,448.31 seconds. Okay, now we need to use some dimensional analysis to convert our units from seconds to units of days. So what let's do first is go from seconds to hours, and then from hours to units of days. So we know that in 1 hour we have 3,600 seconds. So here we have our units of seconds cancel out. Okay, so I'm left with units of hours in my numerator here, and we know that we have 24 hours in 1 day. Okay, so I have this value saved in my calculator here, so I'm going to divide by 3,600 seconds, and then divide that answer by 24, and now I have 686.74 days. Okay? Now, we need to convert from units of days to units of years, and we have a conversion factor. We know that there's 365.25 days for each year. Okay, so I'm going to write my value again, 686.74 days. I'm going to multiply by a ratio that's going to cancel out the units of days. So we're going to divide by 365.25 days. I have 1 year in my numerator. Okay, units of days are going to cancel. And this gives me 1.88 years. Okay? All right, so before I erase all of the algebra that we went through here, we're going to have to calculate the average orbital velocity of the planet. Now, our equation for average orbital velocity is equal to the square root of universal gravitational constant times mass of the sun divided by the average orbital radius. And this is going to be in units of meters. Now, we have already calculated the product of the universal gravitational constant and the mass of the sun. And we did this here in the denominator when we were calculating the orbital time period. So, the product here, we don't have to rewrite it and we don't have to go through all the calculations again. You already took care of that. So let's be efficient here. Our value is right here. So what I'm going to do is I'm just going to write a little note here. G times mass of the sun is equal to 1.32733 times 10 to the 20th, and I have units of meters cubed per second squared. Okay? So, now that we have that value written down, let's go ahead and erase all of our algebra here. So we have the answer for A. So we calculated the orbital time period of our unknown planet in units of seconds, days, and years. Now let's calculate the average orbital velocity of the planet. Here's our equation that we're going to use. Okay, so velocity is equal to the square root, in my numerator, 1.3273 times 10 to the 20th meters cubed per second squared, divided by the average orbital radius. And so remember, we need it in units of meters. I erased it, but it's going to be 2.279 times 10 to the 11th meters. Okay, and let's just go ahead and do the division, and we'll talk about units here. So the average orbital velocity is going to be equal to the square root. We've got a really big number here. 582417727.1. So this is going to be 582,417,727.1. Now let's take a look at the units that we have. So in my numerator, I have meters cubed per second squared. We're going to divide this by units of meters, and algebraically, you know that that's meters over 1. So let's go ahead and divide our fractions. So meters cubed divided by second squared times 1 over meters. So one of my meters cancels out, so this will give me meters squared per second squared. And this is okay because not only are we taking the square root of the numerical value, we're also taking the square root of the unit value. So underneath my radical, meters squared per second squared. Okay? And our velocity, let's go ahead and take the square root of this very large number here. So our average orbital velocity is 24,133.33 meters per second. So it's moving through space at a very high speed. And we'll go ahead and write this value down. All right, I'm going to erase all of the algebra here. Okay, and on part C, it says use solar data table from page 915 to identify the planet. So what we're going to do, so we're going to take our textbook out. We're going to turn to page 915. Okay, and on page 915, at the top of the page, we have solar system data. Now, what we're looking for is the orbital time period, and we're going to see if we can find an orbital time period in 1.88 years or 686.74 days. So we're going to scan through all of our data here. And what we have is the orbital period in Earth days for Mars is 687 Earth days. Okay, so right here. This is it. This is Mars. So we have identified our data. So it's asking what planet. It's Mars because we're comparing the orbital time period data that we calculated to what's in our table for our textbook. So on part C, the planet is Mars. Okay? Determine the average orbital radius in units of astronomical units. So I explained in class the other day, and we drew some pictures on the board. So the average orbital radius of Earth orbiting the Sun is known as 1 astronomical unit. Okay? And so we know that Mars orbits the Sun greater than 1 astronomical unit because it's further away from the Sun than Earth is. So what we're going to do, so we're going to grab our textbook again, and we're going to take a look at page 173. And on 173, it tells us the mean distance from the Sun of planet Earth. And it is 1.5 times 10 to the 11th meters. So Earth's average orbital radius is 1.5 times 10 to the 11th meters. And this is equal to 1 astronomical unit. So what we're going to do is we are going to perform some dimensional analysis here. We know that the average orbital radius is right here, 2.279. So 2.279 times 10 to the 11th. Remember, we need to convert it into units of meters. And then we're going to multiply by 1 astronomical unit divided by 1.5 times 10 to the 11th meters. And we're going to do that so we can go ahead and cancel the units of meters. And that will give us units of astronomical units. So I've got 2.279 times 10 to the 11th. We're going to divide this by 1.5 times 10 to the 11th. And this is going to give us 1.5193 astronomical units. .5193. Yes, astronomical units. Okay? And then in part E, it says calculate the force of gravitational attraction between the two planets, okay? So what we're going to do is use universal law of gravitation, okay? So I have the force of gravitational attraction between two objects is equal to the universal gravitational constant times mass A times mass B divided by the center to center distance squared. And so this is going to be our average orbital radius in units of meters. So in my numerator, I have 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Mass A, so remember this is between the sun and the planet. So calculate the force of gravitational attraction between, I should say, the sun and Mars, since we know it's Mars now. Okay, so mass A, mass of the sun is 1.99 times 10 to the 30th kilograms. And then we need mass of Mars. So what I'm going to do is I'm going to look on page 173 again, okay? And the mass of Mars is 6.42 times 10 to the 23rd kilograms. So 6.42 times 10 to the 23rd kilograms. And we're dividing this by the average orbital radius. So I have right here, I've got 2.279 times 10 to the 11th. We're in units of meters, and I'm going to square that, okay? Now remember, earlier in the problem, we already calculated the product of the universal gravitational constant and the mass of the sun. Right here, 1.32733 times 10 to the 20th, and we have units of meters cubed per second squared. And so what I want to do is multiply that value by 6.42 times 10 to the 23rd kilograms, okay? So here we go, 1.5, okay. Okay, so we're multiplying this value by 6.42, so times 10 to the 23rd, remember that's the mass of Mars. And in my numerator, I have 8.521456 times 10 to the 43rd. And so I've got meters cubed per second squared multiplied by units of kilograms. So that's kilograms over 1, okay? All right, so this is going to give me kilogram meter cubed per second squared, okay? So that's what's in my numerator right now. I've got a kilogram meter cubed per second squared. We're going to divide it by this value squared. Now remember, we have to square the numerical value and square the unit value, okay? So let's do 2.279 times 10 to the 11th. We're going to square it. This gives me 5.19381 times 10 to the 22nd. And we have units of meters squared, okay? Now let's go ahead and divide this here. And this is going to give me 1.64068 times 10 to the 21st. But now what we need to do here is take a look at the units that we have going on, okay? So, in my numerator here, I've got kilogram meter cubed per second squared. In my denominator, I have meters squared. And algebraically, we know that that is meters squared over 1. So what let's do is let's go ahead and divide fractions. So it's like multiplying by the reciprocal of the denominator. So kilogram meter cubed per second squared times 1 over meters squared. We've got 2 of the meters that will cancel. And you know that a kilogram meter per second squared is equal to a Newton. So, the force of gravitational attraction between our 2 planets, and we're talking about Mars and the Sun, is 1.64068 times 10 to the 21st newtons. So, a lot of newtons there. That's a really big number, okay? So, I hope this demonstration, me working through this what planet problem, has helped you today. If you have any questions, please contact me through Canvas or send me an email, or you can call my office phone. So I hope you have a wonderful day. Thank you.